Hello again, Physics 243. Let's discuss sound quality. So the question is, why does a guitar sound different than a piano or a violin? What is distinct? What makes these different instruments sound different from one another? Well, the answer is, here's the key point, the resonance box emphasizes different mixtures of overtones. So we talked about in the previous unit, we talked about how the surface here can resonate. You can have standing waves of different kinds on these flat surfaces, two-dimensional surfaces. And the characteristic shape gives rise to different mixtures of those oscillations. Okay, so we've talked about standing waves on a string like this, and also standing waves in pipes, standing waves in air, right? Well, when you pluck a string, you don't get just one of these, you get mixtures of them. And similarly, when you play a tube of some sort, you get mixtures of all these standing waves. So typically, several overtones are present when a sound is made. And they add together. It's called the principle of superposition. They add together with different mixtures of the different harmonics. Right, so the resonance box picks out some of these standing waves and contributes them with different weights into the sum. So what do I mean by all this? Well, here's the fundamental frequency of, let's say, this string, okay? Or the air in the pipe or something like that. And here's the next harmonic over that, and here's the one after that. If you add all these together, you'll get a shape like this. And so you can have sound generated by a sound wave that looks like this, and then that repeats, right? Well, this is a mixture of these different overtones. And if you contribute a little bit more of one than the other, then you get a slightly different shape here. Like, for example, if you have a lot of F2 and less of F1 and F3, then you'll have a particular shape, then a different mixture of these things. And that's what sound quality is. That's what makes a guitar sound different than a piano or a violin. The mixture of the overtones is defined by the resonance box that's attached to whatever it is that's generating the vibrations. So why does a guitar sound different than a piano or violin? They produce different mixtures of overtones. Here's a clarinet. And what's graphed here is how much of various frequencies contribute to the overall sound that you're listening to. So somebody was playing a clarinet at a particular note or whatever, and somebody recorded the sound, and what you can do is break it into the different frequencies. And the vertical component here is how much of each of these frequencies is present. There's a whole lot of this frequency, some of this frequency, hardly any of this frequency, and then a good contribution from these frequencies. That particular mixture of these overtones is why a clarinet sounds like a clarinet. Here's a piano. Notice that it's a different mixture of overtones. And the violin. Violin has a pretty clean mixture. It's mostly just the fundamental frequency with just touches of some of the other ones. All right, so that's why things sound different. That's what's referred to as sound quality. Now, related question is, why do voices and vowels sound different from one another? Same answer. Let's think about how a voice works. So there's an air source, right, your lungs, and there's basically a buzzer. So your vocal folds buzz when you blow air through them. Right? You have some musculature there, it constricts and you blow air and it makes a buzzing. And then that buzzing goes through this vocal tract here, which includes your mouth. And that vocal tract acts as a resonator, and the shape of that vocal tract causes some frequencies to resonate stronger than others, and therefore gives you a characteristic mix of the overtones. Just like the guitar does, the body of the guitar picks out particular overtone mixture, so does your vocal tract. And the cool thing is that you can change the shape of your vocal tract by moving your tongue around and moving your lips, etc. That's what you do when you speak. This is a neat web page where I got these pictures from. And to bring this home, this idea home, this is how you make different vowels, right? So this is a cross section of someone's head, right? Lips, nose, and this is the tongue. So this is what you do with your tongue when you go from a, e, when you make those vowels, a, e. So try that and notice that you're lifting your tongue. When you do that, you're changing the shape of the vocal tract, right? You're making it narrower up here. Now, when you make different vowels, what you do is you're moving the tongue back and you're changing the shape of the vocal tract in a different location, a little bit farther back. Ooh, ah. Right, so try doing that and you'll see that your tongue makes a different motion. So here is a depiction of the motion of the tongue. So if you look at these dots, right, that's the highest point on your tongue, and it moves this way when you're doing this sequence of vowels, and it moves this way farther back, you see, when you're making this sequence of vowels. And also notice that this purple line here is flatter. Well, actually, that's the same one as this one, but these lines are flatter than these are. So in that way, you're changing your vocal tract. You go, ah, e, ooh, ah. Try that. And so that's why vowels sound different from one another, because the shape of the vocal tract is different, and the vocal tract is the resonator. And so different mixtures of overtones are produced. Now, to emphasize this point, at the Exploratorium in San Francisco, there's this beautiful demonstration. First of all, there's a duck call, which is basically a reed. And some air is forced through it, and it makes a buzzing sound. So I should be able to play it here. Okay, so a little bit of a rude sound, but that's what this duck call does. Now, that sound is then plugged into this piece of plastic. So it's, I guess it's lucite, clear plastic. And what they did is they drilled this shape on the inside of it. So think of a reverse lathe. And this is a model of a vocal tract straightened out, right? It's bent in a real person, but here it's straightened out. And when this duck call is sent through this piece of lucite, this is what it sounds like on the other side. Right? The vowel sound ah. Now, there are different blocks. Here's a different chunk of plastic that's shaped differently, right? And remember that when you made the E, you lifted your tongue up, so you narrowed this part of your vocal tract. And so look what happens when you take the same duck call and plug it into this piece of plastic. Here's O. So just to repeat, this duck call, or rather that sound, is sent into these three different plastic resonators, and you get the different vowel sounds. And again, the reason why the vowel sounds sound different is because these different resonators produce different mixtures of overtones. So it's a very nice demonstration, and they give you a little bonus sound. And that's created with a duck call going through probably this one here. Oops, probably the off. Oh, what happened? All right, so let me come back here. Okay, so that's why vowels are different. Now, overtone singing. Maybe you've heard of overtone singing. This is an amazing, amazing thing. So here are some illustrations of that, which I'll play for you. What overtone singing is well, you sing a fundamental frequency, ah, something like that. And then you shape the vocal tract very precisely so that you make some particular overtones ring out much, much, much louder than others. And you can change which ones ring out by, once again, changing the shape of your vocal cords. Kind of the same way that you produce vowels, except these people can really, really pick out particular overtones. So let me play for you these two videos. Let's see. Here it is. Okay, so check this out, and I'll play a little bit and skip ahead.
Hello, I am Anna Maria, and I'm an overtone singer, and I'm going to tell you something about polyphonic singing today. Overtone singing is a voice technique where one person sings two notes at the same time.
Isn't that amazing? So she's producing the fundamental and then shaping her vocal cords, her vocal tract, in order to ring out those particular frequencies. And she does it so well that you can hear them. And it sounds like she's singing two notes at once. All right, let me skip ahead. In this illustration, she has the same fundamental and she's changing the overtone. But she's so well trained that she can also do this. Let's go to about here. Listen to this. Did you hear the scale in the upper overtone? And the fundamental just changes between two different notes. Play that again.
In steps.
And she does music too. So this is, I guess, a folk song.
Solo voice.
So she can sing and accompany herself. That's amazing. I've seen this live and in person, and it's pretty astounding. Now, this style of singing has been done for centuries in Tuva, and they have their own style. This is somewhere in Asia. They have their own style of singing, and here's a guy that demonstrates 7 styles of Tuvan, I don't know how to pronounce this, Kumi throat singing. So I'll just skip ahead so you can hear some of this. Let's try a different style here. How about this one? I think what happens there is he's able to excite frequencies actually lower than the fundamental, because that really low rumbling sound is just amazing. Okay, so I hope you go to these links and play them and listen to them yourself, because they're really amazing. Okay, so that's it for this one. Next up, we'll talk about interference and beats. All right, see you in the next one.